I'll move the.
So shall I
ZPK.
project? Do you want me to project, and I can and do the clicker association?
For mine, for the chair slides, or
either.
I can do the chair slides.
Okay.
And then for the rest of them.
Okay, fine.
Yeah.
Fine. We're on time. Let's start.
Do you have the chair slides ready? Loaded?
You said do you want me to project? You said.
Yes, project it, but I'll use the clicker. Yeah.
Just and then hold on. Right?
Okay.
Okay.
All right, we're in good shape.
All right. Ooh, hot mic. Okay, is this volume good for everybody? Too loud? Too quiet? Okay. It's a bit of both. Okay, everyone, welcome to the Crypto Forum. If you are looking for another meeting, this is the Crypto Forum. So stay for this if you'd like to. We're happy to be meeting again here at IETF 123. The three chairs, myself, Alexei Melnikov, and Stanislav, who's online.
Hi, everyone.
All right, so just as a reminder, the session is being recorded. We have a minute taker in Headstock. Thank you for volunteering, Scott. And there is a Jabber comment relay. We'll keep track of the chat as we walk through. Just as a reminder, if you need information, this is the participants guide. There's a number of useful links here in the document. Here's the note well. We're pretty late into the week. You should have seen this if you've been to any IRTF meetings. It's very similar to the IETF rights disclosure rules here. So the note well is the same as it's been. So please read it and follow the rules. There's one new point here, which is recently published RFC 9775, which is the IRTF Code of Conduct, which we, as an IRTF group, are under. As a reminder, the IRTF is different than the IETF, works in parallel, but is focused more on research issues related to the internet, as the IETF focuses more on shorter-term issues and engineering and standards. So the IRTF conducts research and is not a standards development org. There's an IRTF primer here at RFC 7418. Let's see. All right, so here is the proposed agenda. It's packed. We have a lot of interesting discussions and presentations here. Is there any agenda bashing from the audience? Going once, going twice? Okay, if not, we will move on from this. Here are some links for the online agenda and the data tracker. This is a quick reminder of some of the things that we discussed last time at IETF 122. Specifically, that CFRG does not standardize protocols for algorithms. It offers foundational research and cryptographic insights to inform standardization activities. And we had some pain points that we highlighted at IETF 122, which is some people want directions from CFRG to be faster, and we have to balance that with being correct. It's difficult to be correct and quick in something as critical as cryptography, but we are trying our best. The second pain point here is there are requests for documents whose primary goal is for immediate implementation guidance or to unblock implementers. This is not necessarily what the group is here for, and this has caused a bunch of pain. So if you have been following the list, there's a couple threads here that really have hit on these same pain points that we highlighted last time. And so on the agenda today, we will be discussing PQ chems, and I'll give a sneak preview to that a little bit later on. So, well, right here, actually. So we are going to have two presentations about PQ chems, one for Entrue and one for Classic Macaleese. This is following up on presentations on photochem and others from previous IETFs. And the discussion here, there's some pretty active discussion on the list, but these are sort of the general questions that we're going to be asking people to think about during this discussion and to bring up points here. So mostly around problem definition for adopting documents and whether we need requirements and how we would make selections if we are going to be selecting specific things. Okay, so we'll go into the status here. Here is, in the bold right here, opaque has just become RFC 9807. So congratulations to the opaque authors. This is a long time coming. It came out of the PIG selection process that was pretty rigorous. So we're very happy with this finally being published. In the RFC editors queue, we have Kangaroo 12, more param sets, and well, opaque. This has been bumped up to RFC. This happened just this week. Nothing currently in ISG review. IRSG review is the AGUS draft, which is coming along. And there are 2 in RG last call that have been updated, AEA limits and DN-HPKE that we're going to revisit pretty soon. Okay, second set here, crypto panel review. We have VDAF and RSA guidance, which are in the crypto panel. The review has been finished on RSA guidance, and it's on to the next step there. And as you can see, there's a lot of active drafts, and there have been updates to over half of them. So this is a really busy group, and we appreciate everyone's effort to help move these things along so we can make room for new work. Here are 2 expired drafts that probably will need to be brought back from the dead here, pairing friendly curves in the BLS signature scheme. But beyond that, we have erratas. We highlighted a bunch of these last time. We had some great feedback from folks on the list to help close these out. Any help that folks can provide to either accept these erratas or reject them would be very appreciated. So there's several few ones from the last IETF, but not too many. All right, so this meeting is, as you saw, the agenda is very full, and we have a 2-hour format, and we had a lot of requests for presentations here. So what the chairs are proposing is that for the next IETF meeting, we have 2 sessions for CFRG. One 2-hour session that's similar to the one we currently have, focused on a lot of presentations about new work and debate and things like that. But we'd also like to add an additional 1-hour session that's focused on ongoing work and progressing drafts. This is part of an effort to move things along more quickly through the CFRG. And also giving more folks a chance to get a presentation on the agenda if they don't, email us within the first few days, which is effectively what happened this time. So this is a proposal. If anybody has any objections to this, you can raise your hand or raise it on the list, but we're happy to chat about that as well. And with that, any other business, any agenda bashing, anything else that folks have? We don't really have time for any other business. So let's get started into the first presentation.
Hybrid chems,
Yes.
01.
Yes. 01.
Okay.
Hi, everyone. I'm here to talk about hybrid chems. This draft is, we have one draft that's been around for a while, one draft that's brand new. I'm going to ask folks to keep to clarifying questions at the beginning, and then we'll have a block for discussion at the end. I'll go ahead and skip the agenda slide. So back in July, a year ago, a little more than a year ago, there was a conclusion of a design team that was expressing CFRG's goals for hybrid chem combiners. Just as hybrid, when we say hybrid, we mean hybrid of a traditional algorithm, something like ECDH or RSA, and a post-quantum chem. So something that will give you security if one of those fails, security as long as one of them is good. So we got this email that went out to CFRG list, which expresses the general goals here, which are laying out security properties we should get, some analysis of how you achieve those, and some concrete instantiations with specific pairs of traditional and post-quantum algorithms. As we've been working on this, some additional, it's in the year since this email, some kind of additional stuff has come up, to generally to provide guidance here that lets working groups and engineers make these combinations, make hybrid chems that are safe and have validated properties, to provide the overall ecosystem some targets to converge on, so that people aren't hybridizing, say, P256 and MLChem 768 in 5 different incompatible ways. We'd like to have some convergence so that the ecosystem runs smoothly. And then as we CFRG have been pondering this, other folks have moved on. LAMPS has written a combiner draft, OpenPGP has written a combiner's draft, X-Wing has started circulating in various places. And so it'd be good if we could kind of consolidate this ecosystem onto kind of a common theoretical baseline. So with that brief in hand, we went off and did some work. So we've got 2 drafts going now that were published just at the draft deadline for this IETF. So we've got a generic doc and a concrete doc. And you can see these, the contents of these documents map pretty directly against what was on the previous slide. So the generic doc lays out generic frameworks that you can instantiate with various sets of algorithms. I'll talk more on the subsequent slide. But it provides the security analysis, that what the goals are, what you need to do in order to satisfy those goals with a set of 3 different frameworks, because you can't choose just one. We'll talk about the number of frameworks in a couple of slides. But yeah, there's basically the engineering work of specifying frameworks, and then a bunch of analysis about how we achieve security properties with those frameworks. Then in this concrete doc, it's a lot, the concrete doc is much less theoretical, much more engineering. It just says, like, here's how you instantiate this with these specific algorithms. So it's just a bunch of numbers and saying, put this stuff here, making things map APIs. So in a little bit more detail, the security goals we've got in the draft right now, the obvious one, big headline one, is of course NCCA. That's the main property you want out of a chem. And secondarily, there are these binding properties that have come up in the literature a little bit more recently about having different variables associated with the chem interaction related to one another. And in particular, I think the ones that we've gotten, the author team have gotten a sense are most important to the IETF, IETF here, are ones where these leak on bounding and the implications from the key to other stuff. And I don't have time to explain what all these mean, but basically these are the properties that say that the key, the shared secret that comes out of a chem interaction is binding on the public key and the ciphertext that went into it. It's very much like a transcript binding property, which you see in tons and tons of protocols. So these seem like the most important ones to go after. So to provide those, we list out kind of the usual set of requirements, basically the things you would expect for these various components that we need to build the hybrid chems. The only one here that's really exotic, and if you've been following the mailing list, there's been some discussion on this, is this C2PRI property, which is, it's an additional property on top of NCCA that gives you access to this QSF combiner that makes it safe to use this QSF combiner that is a little faster than the alternative. So those are the goals. We've got a couple of frameworks that meet those goals. The most generic one is this GHP combiner. We've kind of named them after their names in the literature. The GHP combiner, you just take the shared secrets, ciphertext, public keys, and a domain separator label, shove them into a hash function, and that becomes the shared secret output from the chem. So I've isolated this part of it because that's really the only salient distinction between these various alternatives, including ChemPat you've seen on the list and some other things. So GHP, you just shove it all in a hash function, off you go. The second one, pre here, is a little bit of an optimization on that for a special application case. So cases where your PQ algorithm has gigantic public keys, something like classic Macaulay, where you're taking many, many bytes to do this. And you're reusing them. And so you don't want to hash the same thing over and over again. So there's, you get some performance benefit out of this. I've got some numbers on the next slide. But it's, like I said, pre is a performance optimization over the generic one for that specific use case. And that was based on this ChemPat construction that Bernstein and Josephson preferred. Finally, the QSF construction, which is what X-Wing you may have heard of derives from. It's GHP, but you don't feed in the PQ ciphertext and public key. And so you save on hashing those, and you save some hash cycles. It results in a measurable performance difference. But because you're omitting those things from the hash binding, you're getting hashed at this level into the shared secret, you have to basically ensure that the chem provides, basically these get hashed into the post-quantum shared secret as part of the chem. You're basically trading off this C2PRI feature for having them explicitly in the chem. I probably said that really a little inaptly, but folks can feel free to correct me at the mic later. So we have these three. Folks I talked to about this in preparation for this said, why do we need three? There are some distinctions. So if you are just doing things once, the GHP and pre-constructions don't really differ from one another. But if you're reusing the public keys many times, the pre-construction is quite a bit faster. And even in the case where you're not reusing things, QSF is quite a bit faster, even with quite small public keys. So there are performance differences here that are noticeable, and I believe have been said to be salient by a bunch of application developers. So I think they're worth considering. So yeah, this is one thing I think is worth discussing. You know, do we need all three of these, or what's the right set of things here? In the concrete draft, we have exactly the combinations we were asked to in that email from a year ago. P256 with MLChem, X25519 with MLChem, and P384 with bigger MLChem. Right now, these are all based on QSF because MLChem has this additional C2PRI property that makes QSF safe to use. And what that means is we don't have examples for the other constructions that might be nice to kind of illustrate why we have those constructions. So, I mean, another thing would be useful here is if folks think there would be other combinations that would be useful, other application cases where you want to use a hybrid construction. I think SSH has been looking at classic MacLease, so maybe one of those would be useful. But that would be useful point of feedback from the research group. But this is what's in there now. Obviously, we can add things, take them out, mix them around as folks like. So where are we right now? I think we, the author team, think things are on the right track, let's say. I think we've got a pretty good description of what we've got. So the engineering bits are pretty solid. We've got concrete implementable descriptions of the frameworks. We've got this worked all the way through to test vectors. Boz and I got this even plugged into HPKE and test vectors at that level debugged. So I think from an engineering point of view, we're pretty good. We got a few bugs to work out that we discovered in debugging the test vectors, but to first order, things are doing okay. I think a bunch of the research parts are still are where we need to do more work. So I think we have the outline of an argument and document right now for how these various schemes tie back to the literature and how the security arguments that are in the literature justify the security of the constructions that are in this document. But I think we definitely open to feedback on how to improve those, what we need to explain more clearly. Got some feedback on the list that we need to highlight the need for C2PRI and the risks associated with not having C2PRI there a lot more clearly. So I think that's kind of where we need to do work. Mike, do you have a clarifying question?
No, I'll wait till you're done your slides.
Okay, thanks. And so finally, so this is kind of our assessment, and there are two particular points that we've kind of been operating on. So assumptions the author team's been operating on that I would love to get feedback, confirmation from the working group on. Assumption number one is that it's reasonable to expect designers of concrete instantiations of these hybrid chems to be able to check the C2PRI function, or property of the PQ chems they're using. Because you need to do this if you're going to use QSF. QSF might,
Watson has a clarifying question.
Oh yeah, hi Watson.
Yeah, where do the labels come from? Are they just distinguishing what you put into the combiner, or are they things that applications are supposed to set?
So I believe, so the labels are not specified in the generic document. I believe what we say in the generic document is the label is intended to specify the entire instantiation. So all of the constituent algorithms and the which of these schemes you're using. So it is identifying a whole thing, the specific hybrid chem you're using. And that is what we do in the concrete doc. In fact,
Thanks.
I believe in the concrete doc, those names are the labels, except for the middle one, which is tuned to match the X-Wing label. Deirdre?
Yes, exactly what you just said. These are not to be application configurable.
Yeah.
We are specifying specific algorithm cipher suites, as it were. They are uniquely determining concrete instantiations at a hybrid chem. We had a label for the X-Wing version, and now because people really want to have X-Wing interoperable, the labels vary because one of them had a very particular style and the other ones did not.
Thanks for the question, Watson. So back to this assumptions to validate. So yeah, we want to make sure people are comfortable having at least two options in here. One that is fully generic, plug in any two NCCA chems and it works, and one where you might need this additional C2PRI assumption. So that's the first thing we'd love feedback on. The second one is, there are a few options for pre-hashing public keys and ciphertexts. We went with pre-hashing public keys because you do get a bunch of performance improvement in this key reuse use case. And it looks compatible with the published security proofs. There's no security proofs on the specific construction, which makes me a little nervous. But it seems like it's mostly compatible with the GHP proofs. If you start pre-hashing ciphertext, it gets a little dicier. And so we stayed away from that. So feedback on like what application cases people care about, because these are performance improvements tailored to application cases. So if people care about these reuse cases, care about reuse of keys, reuse of ciphertexts, that would be helpful to know. Or if they don't want to address these at all, that'd be helpful too, and keep things nice and simple. So I think that's all I have. Yeah, we've got two IETF working groups waiting on this to get done, at least two. More if you include like LAMPS and OpenPGP and maybe OpenSSH if they want to use this as well. So yeah, we're really keen to kind of get feedback from this group on what our direction should be, if we're on the right direction, or if we need to revector somehow. But we really want to get this, on a glide path to conclusion. That's what I got. So please end queue for any discussion. Mike.
Hi. Okay, so Richard knows this. This is for everyone else in the room. I'm the author of the LAMPS thing. The LAMPS thing is very close to being an instantiation of this document, which would be great. If the LAMPS thing can say, hey, that CFRG thing, we're a clean instantiation of that, everything's happy, and it should be. And the author groups have worked together for years to make that be true. There are currently 2 points in which the LAMPS thing is not, the LAMPS design requirements conflict with the design laid out in this document. One is the keygen. This one requires a deterministic keygen that just doesn't work with the design requirements in LAMPS, something malbind. And the second one is SHA-2 versus SHA-3. And Deb Cooley had made a very convincing argument like way back in Prague that you don't get to assume that SHA-2 exists outside of your MLChem module. And so I think Joe Salway made a very similar comment. So the LAMPS authors took that as a hard requirement. Richard is now questioning whether that's still a valid requirement or whether we should repoll the community. And if that's not a valid requirement, I'll be happy to change the LAMPS draft to SHA-3 everywhere. So those are the 2 points that I think we need to settle before we can align the LAMPS document and this document.
Yeah, thanks for that recap, Mike. And I think the discussion we'd had, at least among the author team, was that if people were interested in hybrid chems, they were probably also not interested in CNSA 2.0, which is where you get SHA-3 ruled out. And so if we're in a hybrid space, then SHA-3 might be okay. But yeah, I'd love to confirm that with folks. Martin?
Oh, it's Chris. Chris.
Oh, I'm sorry, Chris. Chris, yeah.
All good. Can you go back to the question slide? I just want to. Okay, sorry. First of all, thanks to you and the other authors for like finally pushing this forward. It's been a long time coming. I'm very happy to see it like basically done. So I do think it's on the right track. I do also think it's reasonable to basically look at this new property for chems if they're going to use this particular combiner. I mean, someone who's writing a document that might want to try to use this combiner is probably going to take it to CFRG, and people probably will look at it, and they will probably want to publish as an RFC because that's like historically how this group operates. Whether it operates that way in the future is a different story. So I'm not worried about like people doing it wrong, so to speak. I'm sure plenty of people will look at it and be able to vet whether or not chem does indeed have this particular property that's necessary to use this QSF combiner. And so question 2, I think you should just stick with whatever concrete things you have right now. Those are the things that have definitive use cases. And if a new, concrete Jeff that with motivating use cases were to come into existence, that does the other instantiates the other combiners, I would not object to that. But these 3 have like very real use cases. People want to use them, so let's not like apply Yagni here before before we need to. Thanks again.
Thanks, Martin.
Yeah, Martin Thompson. Everything that Chris said, I don't concretely care too much about the place of the extra hashes here. I think what you have is fine. Again, they seem pretty well motivated to me. But probably the higher order bit here is please publish something soon. Our working group depends on it, and I would like to finish that work soon, as opposed to have it sitting in the RFC editor's queue for forever, because I've seen that happen too, and it's never a great outcome.
Ecker?
Yeah, thanks for doing this. To echo other people, I'm pretty sad that there's so many different options, to be frank. There's a real, the point of the exercise is to provide guides for people to actually use downstream. And if it were me, and so just to put my cards on the table, for me to be exactly one thing.
Ecker, could you maybe slow down a little bit?
Sure. If it were me, there would be exactly one thing, and it would be the safest thing. Now it appears to be the case that there's enough demand for X-Wing that we're kind of stuck there. I'm sad about that, frankly. And if I have more time, I really push on where that was actually true in situations where we didn't where we didn't have like something like TLS where actually didn't need any construction at all. But from what I hear is a lot of people want X-Wing, so fine. Beyond that, I think we should not do any of the optimized things. We publish the safest thing and tell people to use it. And if at some point in the future there really is a demand that you can't use X-Wing and also that you need the pre-hashing, fine. But I think trying to provide this sort of idea for trying to all these options, it's very difficult for people downstream. So my put would be to jettison pre. And as I say, it's not because I have an in for any particular things. I think we should be offering safe guidance to people downstream. And then if there comes a case when we need something that is super optimized, so there's not X-Wing, well, we can burn that bridge when it comes to it.
Thanks. David Adrian.
David Adrian, Google. Just wanted to note briefly that we've implemented one of these schemes in boring SSL. We think that users are more than capable of evaluating the assumptions across each of the different schemes and using them safely. We implemented QSF, the original X-Wing variants. We have, and that's where we're at. At this point, we don't really need a ton of thoughts about anything else. Thank you.
Okay. Dennis?
Dennis Jackson, Mozilla. Yeah, look, I think this is nearly bang on. I think there's maybe some signposting that needs to happen in one of the drafts around some of the things that have come out on the mailing list lately. But other than those very small tweaks, I think this looks great.
Good. Russ?
Russ Housley. We do these homes at the end of the LAMPS meeting or at the end of the composite discussion. These documents are way more aligned than they were before those homes, and let's just get it done. I mean, the things that seem left are mostly bike shedding. Let's just pick.
Thanks. So thanks everyone for the feedback. I think we're at the end of the queue now. So I think we've got, the authors have a bunch of issues queued up in the repo. We're going to do a second spin of the draft and address some of the feedback from the list and from here. Nick, I noticed one thing that was not on your slide about how to schedule time was virtual interims. I think that would probably be helpful for advancing this because I think we could probably get a new spin of the draft in a month or so. I think we could probably get a new spin of this draft in a month or so and have fairly focused questions for the working group to close on.
Sounds good. Yes, we'll take to the list suggestion that we could do a virtual interim in September to nail this down.
Thanks.
Can I make one more comment and before we move on? The concrete instances is not the end all be all of hybrid chems. You can submit a new document that puts your favorite KDF and components chems or components into your own document. We know that we can't fulfill every single requirement with the 3 concrete instances we have. That's why there's been a bit of shuffle between the first draft and what we have now. It's not the end all be all of what you can register or what you can write up. So we hope that the generic document helps you write up any recipe that works for you.
Thank you.
Oh, hello everyone. I'm Harisa of NTT. I will talk about N2. So where's N2? Actually, there are some variants in N2, but I would say N2 are the composition of the 2 variants, HPS and HRSS in this talk. And this N2 is the finalist in the round 3 of this PQC competition. And there are some key features. It's pattern-free, and this N2 has a major specification based on NIST PQC. And almost 5 years has passed after the specification was fixed. Also, it's ready to use. It will be back to review soon. So here's a quick recap of the last meeting at the backlog. I presented that N2 has some advantages over MLChem. And also, there's a good performance and size to compare to MLChem. So due to these features, I said that N2 can be a practical alternative of MLChem. And fortunately, there are some feedbacks, and I'd like to show 2 of them. First, there's a question about other N2 variants, including N2 prime and N2 plus. And I'd like to compare these N2 variants in this talk. And also, there are the opinion about the number of the parameter sets. Actually, there are 5 parameters. After the discussion, we decided to include all of them because this kind of parameters flexibility is one of the advantages that N2 has. But further discussion is welcome for this point. So what are the scope and objectives of this talk? As I mentioned, there was a question about other N2 variants, and also discussion of standardizing McAris and ProChem is now ongoing. So in this circumstance, it's important to clarify the position of N2 among these chems. And we will do some security and performance comparison. And after that, I confirmed that N2 has a tighter security proof and also most comparable performance and size to MLChem. Now first is security comparisons. So I listed N2 variants, FIPS standards, McRae's, and ProChem. And then try to achieve into CC2 security in the quantum model. To achieve this, they use variants of Fujisaki-Okamoto transformation. But there's a difference in the underlying public key scheme. N2, N2 prime, and McRae's use deterministic public key encryption. Because of that, they can achieve a tighter security proof. But the other chems incur security loss in terms of the number of query to the random oracle denoted by Q in this slide because they use probabilistic public key encryption. Actually, N2 Plus is a relatively new scheme, and there's an analysis of indices to security now. So there's another comparison of assumptions they use. I care about whether there is a structure or not. And McAris and ProChem don't use structure in their assumptions. So there are two metrics, tightness and assumption. Actually, macRace is the best because it satisfies both of them. But I think these chems satisfying either tightness or the assumption can improve crypto agility, especially when they are using hybrid chems. So this is a performance size comparisons. This is a supercup measurement. Among these chems, MLChem is the best in terms of the total CPU cycles of keygen, NCAPs, and decaps. Actually, N2 pass is the second. However, as I mentioned, it's under the analysis. And then N2 is the second among these chems. So this is the conclusion. N2 has a tighter security proof, assuming 1 CPA of public key encryption. And also it has a most comparable performance and size to MLChem. So for those who cannot use MLChem, N2 can be a practical alternative. But also for those who can use MLChem, there's a motivation to use N2 because N2 can improve crypto agility with small overhead. For information, there's another draft of hybrid chems in IKV2 using N2. And also we will have a public site meeting on post-quantum IKV2 and then tomorrow morning in Segovia. Yes. And please join us if you're interested. Thank you for listening.
Great, thank you. We're going to move to the next presentation, and comments will come after that.
Yeah.
Simon.
Okay, hold on. Hello. So could you help me with the slides?
Yep, feel free to say next.
Yeah, next slide, please. So I think we're all aware of the problem stated, but it helps to take a helicopter perspective once in a while. So the problem is really we have people collecting data right now, and what are CFRG going to do about it? Next slide. And I think one of the arguments for classic MAC-ELEs is that limiting the selection in CFRG to NIST options is limiting. There are alternatives that are attractive. Next slide. And also a point that keeps coming up for choosing implementation options is that moving targets complicate things and add security risk. Every revision of a chem requires new test vectors, new engineering time, and it delays getting things deployed. And classic MAC-ELEs is a very conservative option here. It has not been patched, and the security has been well studied. So next slide. And there are lots of use cases. That's a question that come up. So people ask, would anyone use classic MAC-ELEs due to its large key sizes and public keys and ciphertext? And there is use cases for it. See the maceles.org page. Next slide. So going into the draft, it's basically just me echoing the public ISO contribution. There is something regarding the naming that engineers should be aware of. In my mind, I've mapped it to that the F and non-F variants are very useful to separate for implementations, but in applications, usually it doesn't matter, and the implementation can choose whichever they want. And there's a recommendation to always use PKChems with a hybrid combiner, pushing the Champat option to include pre-hatching of everything for efficiency. And I think there is a separate work to do HPKE variant of classic MAC-ELEs, but it's going into a separate draft. And frankly, I'm not sure how many people are interested in it, but it seems to be some subset of audience that requests this. And basically, it's a request for adoption and publication to the shares. I think this document is ready and as a stable reference if the CFRG wants to make this a work item. Next slide. And maybe this is a reference page for discussion to keep in mind the sizes that are of importance here. As you can see, the ciphertext are really small, and in applications that can cache the public key, classic McEliece becomes a clear winner compared to many others. Of course, the downside are that, as you can see, the public keys are really large compared to some other CAMs. Although in practice, this is, for many use cases, not noticeable compared to all the other data that go flying by. Next slide. Yeah, these are the folks that actually did any work here. So I think that was the final slide. Happy to take questions later on, maybe if the shares, how you want to have this.
You can stay in the line, and we're going to open up the queue. So we're going to load up the question slide. Just a second as the deck is loaded. Just 1 second. All right, so there's a couple questions on the board here for discussion. Feel free to enter the queue. We're going to have an open 10 to 15-minute conversation and then a number of polls for the audience about this. But the places we're really concerned here and we're raised on the list were first the problem definition. First PQ chems. What's being proposed here is several different PQ chems to be adopted as working group documents that specify them. And so is there a problem that is being solved by adopting a PQ chem for CFRG? And are these problems well defined and well motivated? Question number 2, is the CFRG actually the right venue to pursue the work of writing down already defined algorithms? Is this a good use of the research group's time? Question 3, if we decide it is there a need for a requirements draft for us to sort of narrow down which of the various selections that have been presented would be worthwhile to adopt into the group? If the answer to that is no, then how should we make the decision if not through a requirements draft, or is another mechanism such as a design team like we did for combiners worth doing? There's a number of options here. And then the last point is alternative approaches. So do protocol engineers have the tools that they need to make decisions around which chems? We've heard different protocols making different choices on this. Is there something that the CFRG can do to provide high-level guidance so that general principles important to different protocols can be pointed to the right chem if there's multiple that are adopted? So with these questions, open it up to the group to see if there's any questions, comments, anything to help move this forward, and then we'll ask some questions in a poll.
Richard Barnes. So I would start with this problem definition. So the slide here presumes that the problem being solved is known. It's not clear to me what problem is being solved by this. I suppose the problem, just to hypothesize, the problem might be like there's people for whom the existing standards that are out there from NIST and from others are not sufficient and referenceable. I would love to hear more detail on what people think is missing there. Personally, I have no need of additional PQ chems. Like the stuff that's out there right now is perfectly fine for all the projects I'm working on. If we do have some need for more documentation, I would really want to know, what precisely is the problem we're solving here? Like, what are the open questions that this research group would need to discuss and come to consensus on? Because what I was seeing in the slides here were things like mature specification. Mature specifications are not things that IRTF should be working on. It's not, the IRTF doesn't mean Internet Rubber Stamp Task Force. So if we have a mature specification that's referenceable, there were even some examples of these specs being referenced. I don't know what there is for this group to do. And so I think we need to define the problem and be clear on what there would be for this group to work on.
So you're saying the problem definition is not well defined. The problem is not defined at all, from your perspective.
Yeah, I mean, if maybe I'm just being opaque here, and maybe it's clear that there is some reason that the existing specs out there are insufficient, and this work group needs to do some more. I'd like to get more precision on that if people have thoughts on that. And again, if we do land on that, what precisely is the work this group what the value this group would add?
Yeah, I encourage folks to jump in the line who have a crystal clear problem definition that they think that adopting particular chem drafts will help solve. Next up, Deirdre.
Hi. I understand that there can be desire for diversity of pure post-quantum, quantum-resistant chems besides, your ML chems and the upcoming HQC. Photochem is based on unstructured lattices. If there's a break against MLChem, it is less likely to affect photochem. It's nice conservative assumptions. Classic release is based on other coding assumptions, but Hamming quasi-cyclic is kind of in a similar boat to classic release, not the same, but similar. I understand why people are interested in having these available. I don't know if CFRG is going to be the place to get what they want from those.
Thanks, Chris.
Yeah, I don't love the idea of writing down a program, a primitive that's already been defined elsewhere. I think like we can maybe make incremental improvements, but like I don't know. I really worry about that particular bike shed. But as to like the problem, I guess like one problem we might be trying to solve, or at least one aspect of the problem we're trying to solve, is to help people at IETF decide whether they actually need diversity of computational assumptions. Because like I think that's like, if you talk to a random person in TLS, they might ask like, well, why would I, why and I guess I should say like I was at IPSec today, and it seemed like they're considering like using different primitives, but I don't know if anyone has a clear idea of why. Just that it's like, diversity is good, but why? I don't know. So I think that's something that we can try to help with.
Okay, so on the fifth point here, you're saying that protocol engineers may not have the tools necessary to make these decisions, and that's something the CFRG could help with.
Yeah, exactly.
Great. Yuri?
As to why, probably FUD factor, fear, uncertainty, doubt, has quite a role in this. As for multiplying the primitive, I have questions. One, similarities between, for example, MLChem and NTRU. To me, they look sufficient to assume that if MLChem fails, NTRU isn't likely to hold. More so, considering that GOPA codes can be represented in lattices, if there is an advance in lattice breaking, how likely is it that it would impact codes as well, and a code-based algorithm? I would like the audience to contemplate that and come up with an answer.
Okay, thank you. Yes, the mathematical assumptions of different chems are different, and there's different implications to potential breaks.
It's not just the mathematical assumptions which are different, it's the relationship between those different mathematical assumptions which are not being looked at, being pretty much ignored with uncertain consequences. Lastly, lattices has been studied for what, more than 100 years? Their cryptographic use is what, 30 something years?
Watson?
Hello, Watson Lad, Akamai. I feel that when we're talking about this issue, this is the questions here about who should pick is not really what we're talking about. And the conversation's actually about what does it mean to have an RFC describing a scheme? Why would we have one? And how does that impact usage in other working groups or registration for it? And we're in a situation where the status quo of different working groups proceeded differently to some extent. And at the same time, there was tension between the policies in the IANA registries and what actually seemed to be happening hasn't really worked out. But unless we have a clear understanding of why we have RFCs describing cryptographic things when they're established algorithms, we are not going to have an idea animating our decisions here. And that's, I think, where we need to have the conversation first, so we can all sort of get comfortable, maybe not agree, but at least get comfortable with, yeah, this is why we're going to push these schemes forward and spend the considerable amount of time to make these drafts and advance them. And I don't, I think that there's, some side discussion about certain drafts, certain protocols, certain schemes don't necessarily have a stable enough reference outside here. Other ones, it's described in an ISO document, and if it was used widely, we'll probably want a freely accessible RFC. Those, I think, are good reasons to have an RFC. I don't know that those reasons necessarily apply at this stage versus, hey, we have a code point, we have a reference, we can deploy this. If it gets wider adoption, maybe it makes sense to standardize this, And maybe I'm just hesitant here because of the curves mess, but I do think that we should be responsive to what people actually end up using and try to document what you need to work on the internet rather than try to sit down prescriptively and push it out there, because I don't think that's going to work terribly well. I think we're going to end up spending a lot of time on things that just don't go anywhere.
Okay, thank you, Watson. Patrick's the last comment, and then we will bring some of these questions to the group. So get your Meet Echo open.
Yes. Hi, this is Patrick Longa from Microsoft. Just wanted to reiterate this need for diversity in the toolset of quantum algorithms. It's being acknowledged by several parties, including governments and NIST itself, that we need a variety of algorithms because post-quantum crypto is a relatively young field, and while some people can feel comfortable with the choices that are out there that are being standardized, many parties that are thinking long-term security, they are worried that some of these algorithms could be broken, or there could be IP issues down the road, and so on. So so just to clarify that like many European governments are already moving and pushing for some other options. I think it would be a good idea to include specifically some conservative options that can be added to the tool set of options out there.
Okay, thanks everyone for sharing your opinions on this. It seems pretty clear from some of the feedback where the answers of these are going to go, but I'm going to start a show of hands for a couple of questions walking down this list. So the first one is open. Can you see it?
Click on the chart thing.
It's the second icon beside the chat icon. It's a chart. Okay, so the answers are coming in. It's looking like majority no, but not an overwhelming majority. So question number 2. This next question is CFRG the right venue to pursue this work? And this work being specifying post-quantum chems.
Before answering it, it would make sense to outline what the alternatives are. Do nothing, rely on other standards body. What?
Right. So alternatives here could be highlighted by the recent HPKE group, which is an IETF group, which can write standards track documents and define code points and explicitly put cryptographic things. An alternative to specifying these algorithms here in CFRG as research informational documents, proponents may do what the HPKE group did or go to the HPKE group and create an IETF group for standardizing those. That's an alternative.
And also for the specs themselves, they can go to independent stream editor. But of course, if they still want IETF code points, there will be a second step that needs to be done elsewhere after that.
Okay, it's the yeses are in the majority here, just barely. The polling answer was 16 yes, 39 no, and 14 no opinion. And for the second was 40 yes, 26 no, and 14 no opinion. The next question is for those who said that CFRG was the appropriate venue, do we need a chem requirements document similar to the PAKE requirements document and process to before proceeding with any specific choices? Okay, answers are coming in. We're balancing out. So for the notes, 45 yes, 18 no, 9 no opinion. Okay, and this last question is this could be more of a raise your hand or raise your hand in the chat, but given the suggestions that we had, is anyone here willing to write a meta-analysis draft comparing the security reductions and proofs of different candidate chems? Is this something that, is there somebody in the audience who's interested and willing in writing a draft to help inform protocol developers of what considerations they should take into account? And if so, say yes on the chat or raise your hand in the room. Anybody in the room? If not, you can bring it to the list as well, or bring it to the chairs if that's something you're interested in doing. Okay, with that, I think that concludes our PQ Chems discussions. Thanks everyone for participating. We're going to move on to the next talk. Yeah. All right, blind BSS. Vasilis and Greg.
Yep, hello, can you hear me?
Would you like to control slides, or do you want us to control slides?
If you can control it, that sounds good.
Yeah.
Okay, if you can't do it on your side, just say next and we'll move it up. Okay, move it forward.
Sounds good. Okay, next, please. Cool. So just going to talk about some updates on the BBS signatures documents. There are essentially 3 documents. The first 2 is the core scheme, the core BBS signature scheme, and then a blind signature extension. Core scheme just describes a way to issue signatures over a set of messages and then create presentations from those signatures, zero knowledge based. The blind extensions defines a way for the prover to commit to a set of messages to be included on the signature without the signer knowing them. There has been no changes on the blind signature document, but there have been some changes and updates on the core document, editorial mainly, incorporating some suggestions from the crypto panel review and from various implementers. So this is mainly like clear test vectors, clear pointers for academic work, and so on and so forth. Next slide, please. The third document now, which is the main thing that we want to talk today, is regarding pseudonyms. So a pseudonym is essentially a value that is bound to a signature and is constant in a specific context, but unlinkable across contexts. And this context can be an application context, can be a specific reliant party identifier, and so on. So this provides a way for a prover to have some sort of pseudonymous identity for this specific context, but to retain all the privacy guarantees across different contexts. Next, please. Now, this will become clear on seeing how the pseudonym is calculated, at least right now. Now, a pseudonym is essentially a context-defined point, and we will have to care for that, times a scalar value, which we call mean secret, that is signed. It's chosen by the provers, not known to the signer. And then to create a presentation, you just calculate the pseudonym, calculate a normal BBS zero knowledge proof, and then also a ZK proof of pseudonym correctness, essentially, that the pseudonym is correctly calculated. And this is, your presentation with the pseudonym, and this is what we do today. Now, the problem here is that this compromises a privacy property that the other documents have. essentially, presentations created by the core PBS scheme are informationally theoretic, zero knowledge. It means that even having a post-quantum computer, you will not be able to break the anonymity and privacy guarantees of a BPS proof, even though the scheme itself it will not be secure. So this is, safeguarding against store now and link later kind of attacks. However, if you use pseudonyms, this will be compromised, because if you are able to get the discrete logarithm of the pseudonym value, this is this name secret value, this is signed, this is constant across all your presentations. So if you are able to derive it, you will be able to break the privacy guarantees of this. Next slide, please. Thank you. So our suggestion here is to fix this, is instead of using this one name secret value that is assigned, to use a polynomial evaluation where the polynomial is signed. And when I say that the polynomial is signed, for now I'm just meaning that the coefficients of the polynomial are signed. And then this polynomial is just evaluated as some context specific scalar. Now, what this achieves is that you can essentially, if the degree of the polynomial is n, you will get n different pseudonym usages, meaning that you could use this pseudonym to n different contexts without worrying about being correlated by a post-quantum computer later on. And this is because even if you broke discrete log on the pseudonym, you will just get evaluation of this polynomial at some context specific scalar. So unless you get n plus 1 of these evaluations, you will have no idea of what this polynomial is. Next slide, please. So this is where we need some feedback. First, to talk a little bit about disadvantages and advantages. The disadvantages here is that the size of the proof will increase linearly to the degree of the polynomial. So you have, for each coefficient of the polynomial, you have 32 more bytes on the final presentation, let's say. And this is because we don't use any optimizations here, like polynomial commitments. We just sign the coefficients of the polynomial. A way to battle this would be just to use some bulletproof type optimization to lower the size of the proof. But another disadvantage here is that since you get n different pseudonyms essentially that you can use before privacy is compromised by a quantum computer, there's going to be some extra logic needed in the application to handle the case that you need more usages out of your pseudonym. Where this logic can go, in the relying party, at the user edge, and so on, this will be an application decision. But yeah, we do want to provide some guidance on how to do that on the document if we decide on this approach. On the advantages now, the main thing for us was that we wanted something that was simple to describe and simple to implement. So no new or more advanced cryptographic primitives. We didn't want to go to the zk-snark route or some other approaches. And one of the reasons for that is that from our initial test, this approach seemed performant enough. And you can see some numbers here that are very, an initial performance evaluation just to get an idea. You can see here for proof verification, it doesn't really make that much difference, even for large values of n. For proof generation, if n gets to the 10,000 scale, it does make a difference, but this still seems performant enough for most use cases. But this is essentially where we need some feedback, either from the room or in the list on the GitHub page. Do the advantages here outweigh the disadvantages, and is the performance good enough for applications, and do these parameters make sense? So having 100 or 1,000, different usages or being able to use your pseudonym for like 1,000 different contexts or even 10,000, does it make sense, or do applications need something way larger than that? And next slide, I think that's it. Yep. We'd love to get some feedback. This is just some pointers on the documents and on the GitHub page where the discussion on this new proposal with the polynomial is taking place. And yeah, that's it. Thank you very much.
Any questions? Any questions on the chat, please come to the mic. Going once, going twice. Okay, we'll move on to the next one. As an FYI, we're a little bit behind, so I encourage the speakers to stick to the allotted time for the talk, and we may be shortening the question period.
Thank you thank you to the chairs for inviting me and for giving me the time, and thank you to the audience for your attention. I'd like to tell you about a problem. So there's a desire for zero-knowledge schemes for small identity theorems, and these are two examples. One is from the European Digital Identity Wallet specification, or call for whatever they want to do. The other one is from the European Age Verification. Both of them reference the need for zero-knowledge for attributes about identity. And what do I mean by small identity theorems? I can precisely define that as things that require, let's say, very small arithmetic circuits to define exactly what you'd like to prove in zero-knowledge. There's also a desire for zero-knowledge schemes in the IETF. So this is a quote from one of the chairs from the OAuth committee. It says that I do think there is a general interest in ZK for techniques that are specifically post-quantum secure, and they'd be supportive for a statement that the statement is there exists a desire for ZK schemes in the IETF. There's also a desire for post-quantum zero-knowledge schemes. So this is feedback from both the European Union as well as organizations like Apple and Google. They have a desire to avoid deploying new ECC-based schemes. The preference is to choose post-quantum schemes when possible. And so, for example, the other requirement and other requirements for this case of identity, such as device binding and support for legacy cell phones and so forth, it rules out some of the schemes that this group has considered before. Like, for example, the BBS scheme that Vasilis just talked about, the scheme that Kathy will talk about next in the next talk, which is about Sigma protocols. These are solutions that are being researched in this group, but do not apply to this particular problem and do not solve the problem that the IETF has pointed out. So that essentially brings me to the question that I think needs to be resolved. There needs to be some, and the word specify here is the wrong word here. I apologize for my word choice. The word should be research. There's a strong need to research post-quantum zero-knowledge schemes for these applications. And I think that this place is a logical place based on the prior work. For example, the work on BBS, which was addressing a similar problem, but with different constraints, and the work addressed by Sigma protocols, which is also in the same category, but doesn't satisfy the constraints. And so I guess one of the questions I have for the chairs is there interest, and for the people, is there interest in working on this? I'll tell you the work that we've done. We have written a draft, an informational draft, that describes a particular solution. The solution works with one of the oldest recipes from the literature, which just requires you to basically select these three components: an interactive proof, a commitment scheme, and a zero-knowledge technique, essentially. And for that, we've selected an old one, SumCheck. It's SumCheck based. This is a paper from 1991 with a lot of follow-up work on it, including my own work. And then there's another mini ZK system called the HARO, which is in what's called the IOP model, in particular IPCP model, which is a sub-model of the IOP. And it only requires the use of SHA-256 as its only cryptographic assumption. And so that's why this recipe is kind of what we consider a very good solution to this problem. But again, it's a research question for these type of people in this room, whether there are other alternatives or whether the assumptions and so forth are correct. Again, this system that we propose is robust enough for practice. It can handle statements that are as complex as the one I've shown here. This is not for you to parse in the room, it's for you to look at afterwards. But essentially, it captures one of the real-world applications for mobile driver licenses. And the zero-knowledge proof is efficient enough to run on modern phones in a timely way. Our scheme there's an academic paper, it's open source, there are some external security reviews for the parameter selections, and the high quality deployment has also been verified in the sense that this is a scheme for which real code exists. There's some sort of basic consensus, and so it's not sort of work in vain. And we conjecture that this is the best type of recipe that balances proof size versus work for small theorems, for different settings of small there. Again, the risks to this, there is this research question about proximity gaps. There's a natural question of how we can trust circuits, and there's also code complexity. I wanted to highlight one fact here, which is that just the implementation of the BLS pairing curve is about 11,000 lines. Whereas the complexity of the full zero-knowledge system here that we are proposing is less than 3,000 lines, and each component essentially being separately checkable in less than 1,000 lines. So in terms of that, there are some good precedents for this being a simpler solution than other solutions selected by this group as well. So that's a backup slide, and I just wanted to finish with questions the last 5 minutes. I think I'm on time.
Mm-hmm. Great. Do we have any questions in the queue? I encourage other folks who have been working on related ZK things, potentially related, to chime in. Deirdre?
I really like this work. You're turning me into a big fan right now. Small sizes, small assumptions, efficiency. I really like it. Post quantum. I support this work. That's it.
Thank you.
Watson?
Yeah, I definitely support this work. What would it look like to bring this as an internet draft to the CFRG? Would we need to define some sort of language for circuits and then a way to put those into, get a proof out for the circuit and a witness? I'm just trying to think about the way we would make it so that people could easily implement what we would specify and then integrate into other applications. I've seen that be an issue with a lot of ZK technologies out there.
Watson, that's a great question. We have taken an approach at this. We have published a draft, and our goal was to try to specify things in a way that's not specific to our choices. So, for example, we picked this very algebraic form, which is sufficient to, essentially express efficiently everything we've considered. Also works with R1CS-based ZK proof systems. So we can take that question offline, but certainly we're trying to find something abstract that's not too constrained to what we're doing, and that allows, for example, growth in other IOP-based ZK proof systems.
Chris, last question.
Yeah, I just wanted to, this CFRG in particular, we have a lot of exciting things around zero knowledge proofs. We saw the same thing at the last IETF. It's clear that something is happening, and that's cool. But I really think before we decide to adopt something, if that's the direction, if people want to go, I think we need to figure out what our roadmap is, what problems are we actually trying to solve. So just in general, not a critique of this presentation or this work at all, but just something I've been thinking about.
I appreciate that. Just one correction, though. This is not exciting ZK work. We actually think of our work as boring ZK work. We're taking the most conservative assumptions and using the oldest schemes that we know and using no very fancy math at all. And so it is very boring, but I do agree with you. If you ask me what the very specific problem would be, it is in the first paragraph of our draft there. If you take a look at that, I'd love your comments, which is essentially, if I give you a circuit C that has a public input X and a private input W, and you want to prove to me that C, when evaluated on X comma W, is equal to 0, that's the problem you want to solve. And it must be post-quantum, and those are the rules of the game.
Sounds good. We already have a draft that's like a multi-party computation thing that does something very similar. So yeah, I personally think that's the right problem to solve. So great.
Thank you.
All right, thanks. We'll take questions to the list.
Thank you.
Seems like there's definitely some interest. All right, next presenter is Kathy.
Hello. If I could take over the slides, I can.
Would you like to control slides? Or?
That'd be great. Yes.
Okay, go ahead and tell me next if.
Let's see. Okay, I don't see it yet, but I'll just get started. I'm Kathy. I'm going to present on Sigma protocols. Specifically, this is something Michele presented at the last IETF. And since then, we have had a call for adoption that went super well, and I want to provide some updates there. Do I have control over the slides? Can you hand me control? I don't see that just yet. Anyway, next slide. Oh, perfect. I see that now. Awesome. Yeah, so very brief recap. I'll keep this short because Michele really covered all of this last time. Sigma protocols are a zero-knowledge proof, or specifically, they're the simplest family of zero-knowledge proofs. And so you basically want to prove the statement over secrets and then interact with the verifier until they can verify that statement over some messages. So not going to go into too many details, but I do want to call out that ideally what we want is the ability for developers to define their proof over statement and secrets and not have to worry about what happens behind the hood with all these interactions. So a Sigma protocol is interactive to begin with, and then we apply a fiat-Shamir transform to give non-interactivity. I'm calling this out specifically because there's a little bit of confusion about this. The way I think about it is that the Sigma protocol is like the core, the Sigma protocol is interactive, and then that's like wrapped or transformed by the fiat-Shamir transform, and then the outer layer, like advanced protocols using this, would sort of call into this bundle that is now a non-interactive proof thanks to the fiat-Shamir transform. So hopefully this clears up some questions. I will go into specifics regarding this separation later on. But this is a really widely used building block. I do want to really call this out. This is not us sort of introducing something that is new to IETF or to standards. This is something that is already used in many places in signature schemes, in anonymous authentication schemes, in multi-party threshold cryptography, and many other places. These drafts or specs are already defining Sigma protocols. But the thing that I think is like a little bit like silly or suboptimal is that all of them are sort of defining their own version and their own, like, so to speak, hand compiled Sigma protocols. And it would be really useful for us to define like one way to do it. And then the drafts don't have to sort of hand compile their proofs. They can sort of just specify their statements and their secrets and have that sort of get tossed into a Sigma spec, such as our Sigma spec. So that's the pitch. Yeah, so Sigma protocols are a prime candidate for standardization because of this. They're already used many places. They're very reusable. If we standardize them, we'll have better modularity. And this will be less work for the IETF, everyone implementing, designing, reviewing, auditing proofs, because you could just look at the statements and say, if these statements look right and we trust the like Sigma spec proof compiler, then that's good. That's sufficient. And then also, I just want to call out that the pieces that we use to build the Sigma spec are composable. So for example, or many other protocols might use the fiat-Shamir transform, and you can sort of use that as a piece out of our stack of specs. You can also reuse our definition of the Sigma linear equations. So in case that's helpful, in case other specs, for example, want to define R1CS equations or other linear equations, you can use a similar format. But one thing that I really think is important is that it's better security. It's one place to fix any vulnerabilities instead of having like 10 different specs that all do their own like little variations of Sigma proofs. And you can also have more robust security guarantees if you invest in analysis over one protocol by working with the academic community. So yeah, the call for adoption, it happened. I'll start with our like really happy rainbows and butterflies feedback, which is people just being like, this is great, we support it. There's a lot of support for this as a reusable building block. There's callouts that this is useful across many IETF drafts, pressing need across multiple areas, really great building blocks. So thanks for that feedback. We also got support from deployed privacy systems such as Tor and Ethereum, and these folks they have deployed ZKP at scale and really see that it's helpful to standardize and have these be well studied. And then lastly, there was support from folks working on in-design privacy systems. So UDI, anonymous rate limited credentials, privacy pass, folks from BBS seemed all pretty positive about this. Awesome, and there was also some really great constructive feedback, and I'd like to go over that and how we are following up with it. So as I sort of hinted at before, there was some confusion about the scoping and the relationship between the Sigma protocol spec and the Fiat-Shamir spec. I think with good reason, there was confusion of, is the Sigma protocol we're defining, is that interactive, non-interactive? And so we have sort of addressed this by very clearly defining the Sigma protocol spec that is for an interactive Sigma protocol. And then, as I said before, we are turning that into a non-interactive Sigma protocol with the Fiat-Shamir transform. So hopefully that clears things up. We did explicitly rename the spec to make that super clear. And the second feedback that we got from Luis is that it would be really great to break out another related spec about the Fiat-Shamir transform, just because these two can be fairly modular. And so we did exactly that. We have a separate spec, the Fiat-Shamir transformation, and those are sort of layered together. So thanks for that feedback, Luis. There was some fun discussion about what curves to support. I am sorry I chose a weirdo suite like P384, and we have heard your feedback, and we are going to a more widely used, highly performant curve P256. So thanks for that feedback. We did this both because performance does matter, ease of adoption does matter, and it is safe to do so. So hopefully folks are happy about that. And then we did get some requests. For example, as Greg sort of mentioned in his talk, the BBS folks could use the compressed Sigma protocols, which is a variation of a Sigma protocol that would give smaller proofs, and sort of requested either in this spec or an extended work, can we support that? And also Mary asked if we could have multi-round compatible challenges. So in response to that, I think, and this is my opinion and maybe an open question to the group, I think it would be better for our spec to not include compressed Sigma protocols, just to keep it really simple and keep the scope pretty limited. But to define our linear constraints and our sort of API in such a way that if you wanted, you can implement that API with compressed Sigma protocols, and those two things can be interoperable. By interoperable, I mean you can define the same statements and have those work with the Sigma protocols or the compressed Sigma protocols. So hopefully we can have some, we can work together there, but I would really prefer to keep the scope of this spec as limited as we can. And to Mary's comment, we actually do support multi-round protocols in the Fiat-Shamir transform spec, so that is addressed. And then there are some open questions from the call for adoption that I would like to sort of half post to the group and half sort of inform you of the stance that we are defaulting to taking. Yeah, there's an open question of, can we converge to one design from Thibaut? Yeah, can these existing graphs converge on a single abstraction, or will we have variant proliferation? It's a good question. And from Christopher, that the specs that we see end up having some variant of Sigma that is optimized for the given use case. So I am being opinion and saying like this spec is our proposal for what we should all converge on. And as for different variations that have different optimizations, I actually think I have a thesis that the specs that use Sigma protocols like aren't non-compatible because of optimizations, but because of pretty arbitrary choices that are not use case specific optimizations, such as how do we serialize, how do we order things going to hash, like things that like we could just decide and converge on. However, if you do have specific use case optimizations for your Sigma protocols, do let us know. But I just like haven't seen that as the main source of non-interoperability or divergence. Awesome. And then there's the question of what should we have in scope. Obviously, there's infinite ways that you can define a zero knowledge proof. We prefer to bias again towards simplicity. So with regards to request for compressed Sigma protocols, I would really prefer just, I love compressed Sigma protocols, but I would prefer to have that not in the spec. And then also, should we support composability? Yes, this could be useful, like composition of multiple proofs or composition of multiple statements could be useful, but until we see like a really, really strong argument for why this has to be in this spec, I would also prefer to bias towards simplicity and not include that. And so I think there's also an open question of like, are there any other pieces from the community that you think like really strongly believe should make it into this spec? Otherwise, we're sort of going to try to draw the boundaries at what we have right now. Awesome. So there is also a question of what documents actually want to standardize their use of Sigma protocols. So we do have interest from some authors of documents, anonymous rate limited credentials. Conveniently, I am an author on that. BBS blind signature folks have expressed interest, but there's some concern about how far along that draft is. So that's a little bit like we shall see. And the folks from Google working on anonymous counting tokens have expressed interest. So I think the question here is how do we move the needle from interest to actual adoption? Are there hard blockers? And that's sort of a question for both the people we have interest from and anyone else who's like potentially interested. Awesome. And next steps are, well, I guess as a recap, we had a successful call for adoption. We had lots of support for this being a spec, and then we had good feedback. And I do think we addressed all of the feedback that we got. And we also had some sort of open questions around scope, and the answer to those questions are that we are biasing towards simplicity unless there's something really strong pushing us otherwise. And with all of that, I think our next steps is that we would like to push for adoption. So with that, I would like to open the floor for any questions or feedback from the audience.
Okay, I would like to request getting SHA-384 back or SHA-512 instead. A reason. People chose SHA-384 not because it's a little slower or because it spits out more bits. Yep. Yeah. Correction, P384. Yeah, I see that.
The weirdo suite. Thanks for that.
Because,
I think we can
some users will benefit from that extra security margin, which will not hurt those who do not really need it. It's better to have extra security and not need it than the other way.
Sophia?
Yes. Hi, Kathy. Oh, thank you very much for this presentation. It's really amazing. And this is really important work, especially in regards to the different applications of nowadays of zero knowledge proofs that are being picked up. So I really love this work. I just had a comment on the composition that you had, so especially on and or composition. So those usually depends on if you compose parallel or sequentially. I don't think maybe that it will be too complex to address that in this draft, but definitely in a discussion section or somewhere further, I don't know what, will be good to address, because at least from the cryptanalysis perspective, we have seen many papers that break zero knowledge proofs precisely because the composability was done incorrectly at the implementation level and also at the security analysis level. So it will be great to discuss it, maybe not in this draft, but it will be great to discuss.
Abi?
Great job, Kathy and Michele. I just had one comment based on your request for other features. I've only deployed Sigma protocols twice, once in the Brave browser in 2016, and then once for our threshold ECDSA and threshold BBS. In both cases, we needed straight line extractability for our security proof in both of those schemes. And so, and of course, you can do Fischlin transform or our own transform for that. However, I would consider, if you do consider using this and you do want sort of internet usage, which requires essentially concurrent security, that you consider or at least dismiss with good reason straight line extractability in your transformation, which is easy to do with Sigma protocols and not too expensive.
Perhaps I can take the theory question if you can hear me properly. And in response to Abi's question, I would like to say that we do have analysis for straight line extraction in the algebraic group model. So we can extract. Thank you.
Okay, and I encourage the last three to go quickly.
Hi, I love this. I want to read the drafts. I don't think they're on Data Tracker yet. At least they're not associated with Crypto Forum.
No, they haven't been adopted yet, so these are individual drafts.
Right, but the related internet drafts section, I don't see it there either. But if you have links to them, I'd love to read them. And especially, I don't think this applies to general Sigma protocols, but I'm especially aware of the proving false statements recent paper of taking a GKR protocol and applying fiat-Shamir to it, and you can do some sneaky things if you can do some sneaky things applying a fiat-Shamir transform to a complicated protocol. So that's one thing that I hope we can wrangle nicely in these documents if we adopt them. Thank you.
Thanks. Quick, Dennis.
I'll be quick. Dennis Jackson. Yeah, I thank you, Kathy, for that really clear presentation, and okay as well for the draft. Look, I think this is exactly the kind of thing the CFRG should be working on. This is important. I think you can see a lot of applications for this, and like it's going to take some time to get it right. So I think sooner rather than later would be great. Thank you.
Great, thanks. Moving on to the next presentation.
Thanks so much, everyone.
Yuto Nakano.
Okay, thank you. Hello, everyone. I'm Yuto Nakano. So I would like to share some updates on RockRS. And so RockRS is the AET algorithm, but I will skip to save some time. And in IETF 121, I was asked about the security of the algorithm. So this is the result of the third-party version that I shared in 116 in Yokohama, and third party confirmed that the algorithm is secure against these 5 attacks. Okay, and the one point or one topic that I want to share is the new parallel mode of the algorithm for the even higher performance. And for this, I borrowed the idea from Aegis and implemented 2 parallel modes and 4 parallel modes, which are the RockRS SX2 and SX4. And below is the result of the performance on Zen 4 and Zen 5 architecture. And RockRS X4 can achieve more than 580 gigabits per second on Zen 5. And the next one is the comparison with high A. I'm not sure if this is the correct pronunciation of the algorithm, but the high IA is the new AAD algorithm that is also aiming for the high performance. And the high A requires more than 2,000 bits of the internal state, and this is slightly more than the 1,792 bits of the Rock ISX2. So I compared these two, and also for the comparison, I also did the SX4 results. And in Zen 4, 3 are very similar in performance, and Zen 5, Rock ISX4 is even higher than the high AE. And that's it. Thank you.
Okay, great. Thank you. Any questions? Queue is empty. Okay, thank you so much. We'll move on to the next presentation.
Hold on 1 sec.
Okay, so I'm here to suggest that we should update CHA Poly 1305. So CHA Poly 1305 is the second most popular AAD scheme on the internet after GCM. It's used in all these protocols here, and it's found its way in many cryptographic libraries. Historically, both CHA and Poly 1305 were designed by Bernstein, but as independent primitives. And were combined, and were only combined later in 2015 into an AD scheme by Neer and Langley. Its attractive features are that it's efficient, especially on generic hardware. It's not based on AES, and CHA has stood the test of time as a stream cipher. And today, it's widely perceived as the main alternative to GCM. So why change it then? So in essence, we can both improve the performance and security in a number of ways. Because CHA and Poly 1305 were designed independently, they have mismatching security levels. Essentially, CHA has a security level of 256 bits, whereas Poly 1305 typically has a security level below 106. Not necessarily a problem, but typically Poly 1305 tends to be the bottleneck in terms of security. A number of other issues are that CPUs have changed since the design of Poly 1305. It was designed to be implemented on floating point arithmetic using 32-bit architectures. And however, today, all of its implementations are using integer arithmetic because it's faster. And most CPUs are 64-bit. This makes many of its design properties actually a bit obsolete and wasteful. Since then, also, AAD has changed. We have new requirements on AAD today that have emerged recently, like commitment security, nonce hiding, and release of unverified plaintext. RFC 9771 has a more extensive list of these, which I'll get into in the next slide. And finally, also GCM is changing. So next is looking to update GCM to increase the security level, the nonce size, and also standardizing new AES modes, which provide more advanced security properties, like accordion modes. So if CHA is to remain, or CHA-based AAD is to remain a viable alternative to GCM and other AES-based modes, it needs to be updated and keep up with these developments. So looking into a bit more detail into RFC 9771, we see all these properties, and many of which CHA Poly 1305 does not meet. To be fair, no single AAD scheme can meet all these properties in one go. There's an inherent dichotomy between single pass schemes and multi-pass schemes. CHA Poly 1305 happens to be a single pass scheme, but there's still room for quite a bit of improvement in terms of it could be enhanced with commitment security, variable text sizes, larger nonces, improves multiple user security, and better performance. On the other hand, it's also possible to define a multi-pass CHA-based AAD scheme that could provide more advanced security features like misresistance and release of unverified plain text or root security. However, I did say that like one of the attractive features of Chacha Poly 1305 is that Chacha has stood the test of time. And would we lose all that if we we make these changes? And the answer is no, because Chacha is the only primitive that requires empirical cryptanalysis as a stream cipher. The rest, the polynomial hash, like Poly 1305, is information intellectually secure. And there's nothing special about Poly 1305. All polynomial hashes are information intellectually secure. And the construction itself, meaning the way how we combine Chacha with the polynomial hash, is catered for by the security proof. So for some context, we have a proposal, for example, for an improved polynomial hash called Poly 1163. We did some benchmarks. And our benchmarks show that, for example, simply replacing Poly 1305 with Poly 1163 in this AED scheme in Chacha Poly 1305, we get a speed up of 20% at 16 kilobyte at message sizes of 16 kilobytes. And the speed up is over the whole AED scheme, not just the polynomial hash. And the shorter messages, the speed up is much higher. That's all I have. So I'd be happy to hear whether there's interest here in working on something like that or any other feedback you might have. Thank you.
Thanks. Is there anybody in the queue? Going once, going twice. Okay, thank you so much. Oh wait, we have Scott. Scoffler. Okay, we have two in the list.
Okay. One of the things I noted on the mailing list is this is actually pretty easy to get wrong by not combining the polynomial hash with the SHA-SHA-2 output correctly. To someone looking at a protocol designer, they could very easily get it wrong by doing XOR rather than a addition. So I believe that that would indicate that some guidance from this working group may be warranted.
So the way of combining it would be the same as Poly 1305.
Oh, I'm sure you're doing it right. Just that I'm saying that maybe these guys out there in the IETF may not.
But I mean, nothing would change with respect to Chacha Poly 1305. So it's a different field, but the addition in that part is not done using field addition. It's done in a different group. So it's modulo Chacha Poly 1305 uses uses modulo 2 to the 128 addition. Yeah, of course. That's why I'm here. So that this could be specified, right?
And Scott, as the scribe, you can write that down because it wasn't captured by the mic.
Were there more questions?
That's the end of the questions. Somebody else dropped out of the queue. So thank you so much. We're going to do the last presentation.
I see two people on the queue.
Well, this is okay. We have one in the queue, which is Chris Wood, who's going to be presenting next.
No, sorry. I'm trying to request slides, and it put me in the queue. Don't know why. Can you hear me, Nick?
Yes. Can you do this again? Request
Yep.
slides.
All right. Great. Thank you. Okay. So thanks for the time. I apologize to the animal enthusiasts in the room. I did not bring Gus, so you'll have to be entertained by the engrossing content I have here in this presentation, which hopefully should be up to par with what Gus usually delivers. Okay, so this is on post-quantum PAKES, specifically hybrid post-quantum password authenticated key exchange protocol. We have a specification that's out, and as of yesterday, we have a paper on ePrint that looks at this in more detail. What I'm going to do today is sort of talk about the motivation for the work, and then hopefully get some feedback on where we go with this. So the current situation is that there's a bunch of PAKEs in existence, classical PAKEs specifically, which have been specified and deployed all over the place. So we have SRP, things like Dragonfly, SPAKE2 Plus, even SPAKE. They are around and they are used in production. CPACE and opaque are on their way to being specified. This is a bit outdated because opaque, as of yesterday, I believe, or earlier this week, is now officially specified in an RFC, just in time for the post-quantum PAKE stuff to, I guess, to commence. Opaque is also deployed though in production, so that's good. But the situation with post-quantum PAKEs is a bit different. They pretty much exist primarily in the literature, not yet widely deployed. To my knowledge, no specifications exist for them. And they have a wide assortment of properties and assumptions upon which they're built. So for example, there's this protocol called noise, not to be confused with Trevor's noise. There's a thing called OCake, there's Chic, and these are built on assumptions ranging from like ideal ciphers to smooth projective hash functions to oblivious transfer, things that are difficult to instantiate in practice or oftentimes expensive to instantiate in practice. So our motivation was to have a specification for post-quantum PAKE with the three properties that were important to us. The first of which was post-quantum, confidentiality and authenticity, which we consider to be table stakes if we're calling this a post-quantum PAKE. Augmented, because we wanted it to be sort of a drop-in replacement for existing PAKEs, or existing augmented PAKEs where they're used today, so SRP and SPAKE2 Plus specifically. And you can also use an augmented PAKE in situations where you have a symmetric PAKE. You incur some cost for doing the whatever memory hard function you have for deriving password verifiers. I'll table that for the time being. Oddly enough, we also want it to be hybrid, hybrid in the sense that it hedges against any problems in the cryptographic algorithms upon which these things are built, the protocol itself that composes the different algorithms, or the implementation of these new algorithms or protocols. So we wanted to make sure that if there was a problem in any of these layers, that the sort of protocol still works, still achieves some sort of reasonable security guarantees against a classical computer. And lastly, we want it to be built on sort of standard assumptions, random oracles specifically, and existing primitives like MLChem. We didn't want to introduce anything new or fancy, so as to not entice people to use this thing. The way we did this was by sort of composing a classical PAKE together with a post-quantum PAKE. So the post-quantum PAKE that we have in the spec is called OQuake, not to be confused with opaque. There's really not many ways you can name these things, so I apologize if there's some confusion. So this is really just a sort of more efficient version of the noise PAKE, post-quantum PAKE that was published in the literature, has been proven to be post-quantum secure. Fundamentally, what it does is basically do like a key encapsulation with a freshly generated key. You encrypt this encapsulated key with something derived from the password, and then the recipient will then, with knowledge of the password, decrypt this public key, encapsulate something back, and prove that it derived the corresponding session key according, using whatever transcript properties or transcript method is needed. And then at the end of this particular run, this one round exchange, both parties have a session key with which they can use it to encrypt further data. This optimization over noise has these little gray boxes here. I'm not expecting people to read this. There will be no quiz, but we are using the chameleon encoding that was recently adopted by CFRG for producing binary encoded public keys that allows us to do things like encrypt with simple XOR operations as opposed to group operations. So you could do away with this if you really wanted to, but for efficiency reasons, we went with this. The only requirements that this has, beyond NCCA for a particular chem, this particular construction does have two more requirements for the underlying chem. One of which is that it's what we call one-way secure, and the other which is it's sort of anonymous under a chosen plaintext attack. And I believe we do talk about these in the spec, but they're definitely in the paper, so you can see that for more details. Okay, so the hybrid version then just takes a classical protocol, specifically CPACE, and CPACE for a very specific reason, and composes it with OQuake to produce this multi-round protocol that has the same interface as symmetric PAKE does, and we very cleverly name this CPACE Quake or Space Quake if you don't really pronounce it that way. Both parties input a password and they output a session key. And you might be wondering like how you compose these things, and in practice what happens is they run sequentially. So you'll basically run CPACE with the password as input, and then take the output from that and shove it into OQuake. Basically the session key becomes the password for OQuake, and then you'll run OQuake on top of that. And then you'll hash both session keys, both transcripts together, along with some other auxiliary stuff, and then you'll output a session key. And the reason for this composition is very important. So CPACE has to go first, in particular because CPACE currently has no key confirmation message baked into the protocol. And as a result, if you were to break CPACE, if in contrast you were to use a protocol that had key confirmation or basically an oracle to check whether or not you had the correct password, you could just target that with your quantum computer and easily break it. So CPACE does not have this property, so it can be slotted in first, and then run directly with OQuake after that. And the sequential nature of these things, as opposed to, you might think like a parallel nature of these things, is also very important. If you were to, you might intuitively think, well, why don't we just run like CPACE and then OQuake, side by side in parallel, take the session keys, combine them in some blessed way, and output the session key. The reason you can't do this is because effectively you reduce the security to the worst of the two PAKEs that you're running side by side. Like you would, if you're quantum capable attacker, you would just attack like the classical PAKE, learn the password, and immediately use it to either log in or to break the other one. So the order here is very important, but the order here does have a sad side effect in that it reduces or introduces another round trip, which is undesirable in many cases. Like if you were to plug this into TLS, for example, you would have another round trip, which is perhaps not the greatest. Okay, and our even more cleverly named hybrid or augmented version of this is a Space PAKE Plus. The plus is synonymous with augmented PAKEs like Space 2 Plus. The high level concept is basically to take the hybrid SpaceQuake protocol that we have and bolt on at the end of it a password confirmation protocol that runs in one round. But due to the way you sort of stitch things together, you're not actually introducing another round trip, full round trip. You're just introducing one more message back from client to, or from prover to verifier, rather. And the password confirmation protocol is basically a very simple exchange in which the client proves knowledge of a password that has been previously registered. So in the augmented setting, I suppose I should have covered this, but in the augmented setting, you register a password early on, at some point offline, and then you use it, knowledge of that password to authenticate later on in such a way that the server does not learn the password. Effectively, how this works is you use the password to deterministically derive a key pair, and then you do some challenge response, encapsulate to this public key, prove that you can decapsulate with the corresponding derived secret key, and that's at a high level that's functionally how it works. The details are of course a lot more intricate and nuanced, but that's all you kind of need to know. Okay, so it does have a number of limitations, I'll say. The first of which I think is the multiple rounds. This does make it quite difficult, again, to integrate into something like TLS, which has been accustomed to completing everything in a single round trip. There is a draft that's undergoing adoption, or an adoption call right now in the TLS working group for integrating PAKEs in general into TLS 1.3, starting with SPAKE 2 Plus, but it could easily be extended to something like CPACE and OPAKE. And if we were to add this as an additional, the specific protocol as an additional, supported PAKE in that variant, you'd have to have new handshake messages derived to like carry these additional round trips messages between the client and server. So it's just more of a pain. It's not impossible, but it can be done. And I guess another limitation is that there's like some small minor dependencies beyond MLChem, even though I said at the beginning, like we wanted to use standard primitives. So for our optimized version of noise, which we call Oakwake, we do have this binary encoding thing that we use, helpfully provided by the Chameleon draft. But happily, that's well on its way to being, reviewed, analyzed, and hopefully will be specified soon. So maybe at some point in the future, it won't be quote unquote new. Okay, so of course, check out the specification if you're interested. Check out the paper if you're interested in, I guess, the security arguments for these things. There's a line of work that demonstrates that this sort of direction is the sensible direction if you want indeed a hybrid augmented PAKE, post-quantum PAKE. So I guess my questions for the group are, first and foremost, is this work of interest? Be it the hybrid version, which has these multiple round trips, or even the non-hybrid version itself. If you wanted to just plop in a post-quantum PAKE Oakwake specifically, or I guess not specifically. We could the group, if it decided to do this work, it could come up with something else. And then should a specification for this happen inside or outside of the CFRG? Historically, PAKEs have been, a topic that have taken place in the CFRG. We had a PAKE competition to select two, one symmetric, one augmented. That process was effective, it completed, and the final RFCs are almost are halfway done, I'll say. But it's also plausible that this work happens in an IETF working group outside of this group. Because you are kind of, just specifying a protocol and less like a framework, so to speak. But nevertheless, if it happens inside the CFRG, I think there's a very clear path to doing that work. The draft right now is written in such a way that it provides a solution to a sort of assumed problem. The new process that we have sort of requires us to take a step back, first articulate the problem a bit more, what the solution space might look like, why things like ideal ciphers are not reasonable to implement in practice or cannot be implemented in practice, and why you need something more different, and then potentially these protocols being solutions to that particular problem, sort of like what we've done with the generic and concrete hybrid chem draft. So if people feel like CFRG is the right place for this work, we can absolutely take on task of producing this sort of more general document. That's very possible.
So Chris,
and if it happens
we're just over time right now, but if somebody wants to ask a question, we can do it. But these are really good questions to take to the list. If nobody else wants to join the queue, we have one question on the queue, and we'll let you go. Thanks, Chris. Apologies for cutting you short.
It's okay.
I think I'm just about to express an opinion that a lot of people express in chat, which is like PQ PAKE would be great. It's the next natural thing to make PQ. I'm definitely concerned about the extra round for making it hybrid. I'm sort of the opinion that I probably don't care about hybrid for this, or at least I don't I don't think we have the same motivation as we do, say, for like key exchange and TLS. And then I wanted to hear about, like how does this compare to like generic combiners? I know that people have looked at this, at least in the academic literature. So yeah, if you have thoughts there, that'd be great. But also we're out of time. So answer whatever question you want or don't.
We can take it offline. Thank you, Chris.
Okay, thanks everyone for attending. Have a good rest of your Thursday.